Alright, hello everyone. I am Professor Caudill, and we started on chapter 4 yesterday. So we got through parts, I think we got to the part with some calculus. It's kind of a ways down. Yeah, I think we stopped here last time. So just to review, you can find the total displacement. You find a displacement vector. So this has a angle and a magnitude. So you can separate, you can find the magnitude by taking all of these, Pythagoras theorem. You can find the angle with the trig function, SOHCAHTOA. Okay, so previous chapter we talked about instantaneous velocity. So this I haven't seen this before. I haven't really worked with vector functions. I worked with like regular functions. Um, Not sure what exactly the difference is, except for it's like a matrix of smaller functions or vector of smaller functions. All right, so they're showing how this is done. So vectors are traditionally linear. So vectors are not curves typically, but you can calculate the point, the y coordinate based on a function. So I think that's what they're trying to do. So R is okay. So I see why they did the displacement before. So you need to understand displacement because when they take the derivative, it's like the average. It's like taking an average infinite times at infinitely small intervals. So this is like a resultant. This is you see you're taking this minus this, and you're getting this, and it's for infinitely small changes in time. So when you subtract this vector r by just rt, you're going to get like a difference of whatever delta t is. All right, so they do the b average as well. Nothing that's too unfamiliar. All right, so let's try this one. RT is 2 t squared I plus 2 plus 3 t j plus 5 t k hat. That's all in meters. Okay. So so I'm guessing I could just do like a Newtonian notation, right? R with the arrow above. So R with an arrow and a dot for the first derivative. So that would be 4t. All right, so I guess we have to be specific. Two plus 3t, so that's going to be 3. And this is 5. So they want to know what's the instantaneous velocity at 2. So this is at 2. So that's going to be 8. These will be the same. Average velocity, okay, so we're going to have 3 seconds. This at 3 seconds is 12 and 4. So V average is okay, so it's going to be 12I okay, this minus all of this divided by t, so that's 3 minus 1. So V average is going to be 4I. So did I get it right? Not quite. So got these right. 4I, 4t, 3, and 5. So we got part A correct. I must have just missed reading the speed. So you would have taken 8 plus 3 plus 5. So yeah, so 8 plus 3 plus 5, square root. Sum the squares, square root of the sum of the squares. It's kind of a mouthful. Okay, so what happened here? So V average is R. Looks like I plugged in V. So V should have been 2, 3 squared plus 2 plus 3, 3 plus 5, 3 minus 2, 1 squared plus 2 plus 3, 1 plus 5, 1. And then you take that divided by 2. So I'm looking at 9, 18. 18 minus, so this is all negative. Okay, so I'm looking at 18 minus 4. So I'm looking at 14i minus or plus 0. Okay, and then 15 minus 5 plus 10k. So is that what we got? So we have to take this by 2. That's 7i plus 5. Okay. Okay, so not quite. So this should have been 2, not 4. This should have been 2, not 4. So that would have given us 16. This would have bumped us up to 9. So it would have bumped us up to 16 divided by 2 is 8. So this should be an 8. So they got 11j here. So 9 plus 2 is 11. Okay, so it should have been 11 minus 5, which is 6. 6 divided by 2 is 3. Okay, and then here we got 5, so we got that right. So in a way, it's you're kind of thinking of R as kind of your position in 3 dimensions. Let me see if this is a convention. My textbook and is this a normal convention, or do some textbooks use S? Vector S of t instead. S because it's less common. Okay. RT is more common. Physics. So if that's the case, I wish they would have just kind of kept it in the earlier chapters. Because in the early chapters, they have position function as x. Obviously, that gets confusing when you're taking the derivative. All right, check your understanding. Let's try this one. R. Okay, it's instantaneous velocity, so R is Okay, so it's going to be 9t squared so they want r at t is 2 would be 4 times 9, 36. Okay, and R, so that this is another way of saying V, T or V. Maybe it should, maybe specifying it's a function does matter, because if I just wrote V, then that just might be recognized as a column vector. So I think we probably should specify it. So this is V2. Most of the time, instantaneous and average velocity are not the same. Okay, so I'm reading that, so word here is average velocity. Okay, so they want to know if it's the same, so we're going to do the original position function. So we're going to do r 4 minus r2 over 4 minus 2. So that's going to be 4 cubed, 4, 16. 16 times 4 is 40, plus 6 times 4. 16 times 4 is 40, plus 6 times 4. 64 times 3. 64 times 3 is 612, 180, plus 4 times 3. It's 192 minus R2, which is going to be 4. So minus 4. So that's going to be 188 over 2. So that's going to be 94. Can I do that? This would be I, this would be J. Right, so it's not quite right. So it'd be 192 I plus 4J minus 2 cubed, so 2, 4, 8, 8 times 3 is 24. 24I minus 24I plus 4J. Okay, so that's going to be 172 minus 4, 168 divided by 2 is 84 I plus 4J. Okay, so we see the average velocity. Average velocity is, looks like they're not writing this as a function. So average velocity is 84I plus 4J. So you have to realize average velocity, it's not really using any calculus because you're using discrete values. Um, this is this is like this is like taking the average, but it's in infinitesimals. So you can see how this function is kind of like this one, except you're adding it by delta t, dividing by delta t. So uh, mathematically, the instantaneous velocity is more accurate, but physics breaks down at certain scales. So that's why you should know both. Like if you're measuring at Planck's constant, um, so far I think you can't go smaller than a Planck's time constant. Can't slice time down into anything smaller than Planck's constant. So that's where you would use V average if if necessary. Motion along the x direction has no part of its movement along the y. So they're independent. So three-dimensional object, it's just like the vector chapter, all the videos we did on lectures. It's all about breaking it into component parts. Separate independent motions. Okay, consider a woman walking from A to B in a city with square blocks. Okay, so I don't know how to draw this from what I've started with. Another set of blocks arrive. The woman taking the path from A to B may walk east for so many blocks and then north. Okay, so it's just saying like her destination is here. So she could go this way and this way, or she could have saved some time and took the hypotenuse. I think that's what they're basically saying. Uh, so yeah, and I think this does work for oblique triangles, like anything that's not a angle. We have to do like a more complicated Pythagoras theorem. Okay, so in the kinematic description of motion, we treat the horizontal vertical. So they're talking about one baseball is dropped from rest. At the same instant, another is thrown horizontally, the same height. It follows a curved path. Well, I mean, technically, they're both curved paths. It's just this ball is can't really see the curve, but it's still curved. Like curves can be straight if it's going straight down. And also, like Earth is always spinning too, so always that motion as well. So you see there's two forces on the ball, direction through it, and then there's acceleration, accelerating down. So you can separate these functions. Air resistance, and the Earth also spins, and that affects things like satellites as well. Or I think if you're really big into like sniper rifles, I think the spin of the Earth also affects if you're shooting like longer than 500 or 1,000 meters. I think snipers have to calculate the spin of the Earth because it does have a small effect, not as much as air resistance. Okay, so now we're going to section 2, acceleration vector. So we're gonna find acceleration vector. So it's going to be, I mean, it's pretty obvious. We're gonna take that velocity vector we just learned about. We're gonna differentiate that, and you can just bet it's going to be that. So motion of particle, constant acceleration, 3 dimensions. So I'm guessing the book's gonna keep the same constant acceleration equations. So that's nice for our calculator. It means we don't have to like change much. We'll have to totally rewrite it if we decide to use it. Okay, so addition to taming, displacement vector, no, it's acceleration. Okay. So I'm happy they spell out the definition of derivative here. Um, when you start thinking in limits and like what happens when like a variable is taken infinitely, it it has like good applications outside of math, um, especially like philosophy. If you're taking like a concept in philosophy and you think of it like in the limit, like if we digitize our minds in a limit over time, how do we deal with the heat death and the big crunch from killing us? Like assuming like I don't like when transhumanists say like they become immortal when they digitize their mind. because there's like actual physics theories that say it's not as simple as leaving the biological body. Like the universe is expanding and it's going to expand so much where there's no more energy or heat can't escape. Like heat can't be destroyed, but it can be stretched to the point where um, no particles can interact. Yes, particles can hold energy, but energy and information it can't be transmitted in a big shell. So that's why thinking in limits, when you think of like infinite time or you know just it expands your horizons. So the limit. Um, the one thing I don't like about this book is it doesn't say like limb. Like a high school student, it might be like limb, limb. Okay, limb. They might not know it's short for limit. So that's one criticism. It's not huge, but so they're doing the same thing here. Velocity in the x direction, I, and yes, you can do this as well. Let's take the original position function. I think we should be pretty comfortable with this. I think so. Let's try this example on our own. So velocity, particles velocity of 5 ti t squared j hat minus 2t cubed k hat meters per second. Okay, so obviously acceleration is going to be a constant, or it should be a constant. Maybe not in this example. So it's 5 plus 2t minus 6t squared. Okay, so they want what acceleration at t, so we're going to do a t is 5 plus, sorry, a of 2 is 5 plus 2 plus 6 2 squared 5, so it's going to be 9 plus 4 times 6 24. It's going to be 33. Magnitude and direction. Okay, so I guess this isn't necessarily right. Should be 5, so that I should stop. I should get out of the habit of doing that, but you can't really add these together. These are direction unit vectors. But we can, so we can take the norm a2. So that's going to be square root 5 squared plus 4 squared plus 24 squared. So we're going to scroll down to vectors. All right, so 5, 4, 24. So I'm getting 24.8 of a magnitude. Okay, and they want the direction, so direction. So now that direction is a hard one. So normally trying to think. I know we're going to use tangent theta. Let's do the XY axis. Okay, so it's going to be I want to like my gut's telling me it is 4, 9. So theta xy inverse tangent of 4, 9. So, and then I think you would do the same tangent xc. I'm really not sure, but just from guessing, I'm thinking it'd be 24 over 9. So let's see if the book got that. So 24.8 got that correct. Direction. Okay, so they kind of just skipped on the direction. But yeah, whatever. We'll move on. No problem. Okay, so particle has a position function of ten t minus t squared I plus 5 tj plus 5 tk hat meters. What's the velocity and acceleration? Okay, so velocity is 10 minus 2ti plus 5j plus 5k. What is the acceleration? A is -2i plus 0 plus 0. Describe the motion from t 0. Not sure what they mean by describe the motion. I mean, we could find the magnitude, we could find uh, vt 10 minus 2t 5j 5k and -2i meters per second. Position vector is in blue dots. trying to figure out where T6 is here. So it's 0 seconds. Okay, so let's see if we can. So I really like how they graphed this. Here, each. I don't know if that would fix it. Hmm. I mean, it kind of looks like that. Kind of looks like the graph. It's kind of hard to see. I know there's a way in Senpai where you can make it like an interactive graph, but that might take a couple hours for me to get working. So okay, so A P is A I C K hat. What can be said about the functional form? What can be said about the functional form of the velocity function? Okay, so you're going to take the integral of t dt, which would be a T I plus B T J C plus constant. I guess I can put D. It's multi-dimensional motion. Three-dimensional motion is equal to three one-dimensional motions. Component has a separate, each component has a separate set of equations. Similar for each chapter. We show only the equations for position in XY direction. Z direction. Okay. So I'm thinking they're using the X, like the X axis as a pivot, so it'd be like XY or XZ. But maybe not. Maybe they do YZ. Okay, so this is the set of equations. So X T the average times T So I'm debating if I should put these in LaTeX form. I wish they would write the other set of equations for the Z direction, just to spell them out. Um, So you can see after here, it kind of just repeats. After 4.14, looks like it just repeats. So really it's only four equations. Four equations. Okay, so 4 equations. It's going to be, I like to think in n dimensions. So we're going to say this is x of the n dimension plus x naught of the n dimension plus the average velocity of the x this should be x of t. So that'd be x of n. Xn times t. Okay, so this is 1. Okay, so then velocity of x of the nth x dimension is v naught of the x of the nth dimension plus a of the nth dimension times t. And this might be just making it more confusing than it needs to be. xt is x naught nth dimension so this is f3, this is f4. Okay, so I think you get the point. It's really just four equations. Okay. We got about 7 minutes left. So figure 4.10 shows a sphere. Okay. So we want to find x and y components. Okay, so A is 2.1. Okay, so V 0 is 4.1 I minus 1.1. Okay. So we know the integral of V naught dt is going to be 4.1 t, which is 0, minus 1.1 t, which is 0, plus a constant. So the constant is 2.1. So C1 equals 0.1. That might be completely unnecessary, but I just wanted to see if that would work. So we want to find x and y components. So we want to find, we know, r of 0 is 50j. Okay, so xy components. So can I get the xy components from this? So they're doing the trig thing. We've done this many times. It's hard to kind of see it. Like I know I can do the math. It's just putting everything together into a coherent picture. So they get the acceleration of x and y. Okay, so I guess step one is to convert this to xy. So we know she's getting accelerated, but we want to know what's the components of that. Okay, so then what do they do with the ax? Plug that in. So they plug it into 4.12 and maybe 4.14. So this is saying the velocity in the x direction is 10 at 10 seconds is 24. This is saying the position of the x direction. So then they're going to do the y, the same for the y. So the position of her altitude or y at 10 seconds is -88. How fast she's moving in the y direction is -65. So they put this together into 216 minus 88. So position, they match the positions, then they match the velocities. 24 minus 6.5. Okay. It is useful to know, given the initial conditions of position, velocity, acceleration. Okay. About out of time. I guess I'll end it with this interactive thing. If it works, these are kind of hit or miss. So I'm debating next video if I should start making a Jupyter calculator. This is kind of cool. You can see the acceleration changes depending on where it's at in the ellipse. Um, Not sure what this is doing, but yeah, it's pretty cool. Yeah. All right. So it's a good place to end it. Thanks for hanging out, guys, and I'll see you next time. We might start on 4.3, or I might take a shot at writing some code. We'll see. All right. Goodbye.